We often forget the enormous power of our home star, the Sun. We were reminded of that power on November 29th of last year, 2020, when NASA's Solar Dynamics Observatory recorded a powerful solar flare entitled the Anemone Eruption. Welcome friends, Dr. Jim Daly of Astronomy for Change here, your host, bringing you this dazzling display of our home star's power. You may be wondering why the Sun looks dark and quite unfamiliar. The orbiting observatory records the Sun's light and emission at different colors, known as wavelengths, from different depths and at different temperatures in the solar atmosphere. The Sun and all stars don't have a solid surface. The outer layer, what we see as the solar disk in the sky, is known as the photosphere. We begin this video showing the Sun in three separate wavelengths in the extreme ultraviolet part of the spectrum, color-coded to indicate temperature, with the flare erupting to the lower left at the 8 o'clock position off the solar limb. In these opening frames, the light you see originated from much hotter layers, well below the photosphere, emitted from gas with an effective temperature ranging from 50,000 to 2.3 million, and finally to 12 million degrees. By comparison, the effective temperature of the photosphere is a paltry 5,780. The eruption was nicknamed Anemone since the apparent shape and behavior of the superheated gas jets and filaments are shimmering, as it were, like an anemone. The Solar Dynamics Observatory is a space-borne solar observatory that has been on orbit since February 11, 2010, continuously recording the Sun in 10 different wavebands, and was the first mission launched in the agency's Living with the Star, or LWS, program, a program designed to understand the causes of solar variability and its impacts on Earth. The orbiter has three separate instruments on board: the Atmospheric Imaging Assembly, or the AIA, which consists of four 20-centimeter or 8-inch diameter telescopes, filter and camera combinations that are bringing the Sun's dynamism to life in full 4K detail. The EUV, or the Extreme Ultraviolet Variability Experiment, or EVE for short, to explore the extreme ultraviolet emissions. And the Helioseismic and Magnetic Imager, or HMI. In the close-up video frames recorded in 4K high definition, we observe coronal loops that originate at the photosphere and arc, in this case, to an altitude of 48,000 kilometers into the solar corona, and subsequently return to their origin. To get a better sense of size and scale, the Earth is represented to scale in the lower left-hand portion of the screen at the 8 o'clock position. Temperatures in the corona, the hot, outer, tenuous atmosphere above the solar chromosphere, are measured in the millions of degrees. The chromosphere is a layer just above the photosphere that's a little bit hotter than the photosphere, and that leads further on up to the corona. What we're observing is the highly charged superheated gas as it follows the powerful magnetic lines of force originating deep in the solar interior. It is these magnetic lines of force that breach the photosphere, interrupting the transmission of heat from the solar interior to the photosphere that causes sunspots, regions on the photosphere that are thus slightly cooler and appear dark by comparison. This solar flare was followed by a giant cloud of superheated gas and magnetic material known as a coronal mass ejection, or CME, a type of solar outburst made famous in 1859 and subsequently became known as the Carrington event. The solar material hit Earth's magnetosphere and induced the largest geomagnetic storm on record, resulting in strong auroral displays and causing large-scale disruption of the newly developed telegraph systems of the day. The associated white light flare in the solar photosphere was observed and recorded by British astronomers Richard Carrington and Roger Hodgson. Fortunate for us, last November's solar eruption was not oriented towards the Earth. Otherwise, we could have experienced another powerful geomagnetic storm, complete with power outages and strong auroral displays. The sun's internal dynamics are manifest during solar cycles, a period during which internal solar activity rises to a maximum and then to a minimum over an 11-year period. A rise in internal solar activity corresponds with a higher frequency of solar eruptions, as was witnessed on November 29th, and an increase in sunspots. Since a new solar cycle began in December of 2019, we will start to see a rise in these types of eruptions, with this cycle's solar maximum occurring in the summer of 2025. What we want to do in this clip is to illustrate the correlation between the internal activity of the sun and the rise of solar activity throughout its 11-year cycle, and how it's manifest on the photosphere, or the upper layers of the sun, as can clearly be seen in this composite video of 3 separate regions in the extreme ultraviolet part of the spectrum of the sun. This is an additional set of 3 wavebands. We're going to take a look at this. This is the same period of time in question as this video. See, there you can see the flare. It just erupted. Okay, this is a separate set. This is a separate composite video. This is an additional 3 wavebands in the extreme ultraviolet part of the spectrum. Okay, so what we're going to do now is illustrate this, superimposing this on top of the white light image of the sun, and repeat this exercise. Okay, so here we have this composite video of the separate set of 3 wavebands in the ultraviolet part of the spectrum. Is going to be superimposed on top of the visible white light disk of the sun that we usually see, with the sunspot clearly visible, the sunspot group clearly visible, also combined with the chromosphere, the region of the sun, the layer of the sun just above the photosphere, between the photosphere and the solar corona, whose temperature, although it's quite rarefied, is measured in millions of degrees. So let's take a look. Okay, so you can clearly see the superimposed ultraviolet view of the sun on top of the white light, or the normal view of the sun. You can see the sunspot group aligned with the solar disturbance as manifest by the composite video. The 3 waveband composite video, you can see the group and the sunspots as a direct physical correlation between the solar disturbance, the disturbance that's clearly visible. You can see the solar, eruption just occurred, the solar flare. Okay, and the sunspot group. This is the chromosphere. The solar chromosphere, the region just above the photosphere, between the photosphere and the solar corona. Okay, this is typically about 1,000 degrees hotter than the photosphere. You can see the white blotches. You can clearly see the solar disturbance along with the sunspot. As we know, the sunspot is caused when the powerful magnetic lines of force originating deep in the solar interior breach the surface of the photosphere and interrupt the convection of heat from the interior up to the surface. Okay, that gets broken, and thus we have an interruption of energy flow and a cooler region, generally only a few hundred degrees, but it's enough such that we see it manifest as a darker region on the sun. The opening sequence combined light from 3 wavebands in the extreme ultraviolet part of the spectrum, originating deep in the sun where the gas temperature is above 10 million degrees. All these images and video are color-coded to indicate wavelength, as ultraviolet light does not have a color per se. Dark regions indicate no emission in the waveband temperature being observed, and thus a gas with a specific temperature is visible, and that is what we observe. The teal-colored superheated gas jets and filaments are shimmering with a temperature above 12 million degrees, while the red and gold range between 50,000 and 630,000 degrees respectively. This video was produced here at Astronomy for Change from public archives, available at NASA's Guided Space Flight Center's Solar Dynamics Observatory web portal. Links to these data, video and images, as well as musical score and all content and attributions are available in the accompanying description. If you enjoyed this video or found it useful and/or educational, please like, subscribe, and share. This is Dr. Jim Daly of Astronomy for Change. May you come to love the stars too fondly to be fearful of the night. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized. If you found this video helpful and educational, please like, subscribe, and share. Also, why not consider supporting us on Patreon? Head over to our homepage, astronomyforchange.org, click Support Us via PayPal or Patreon, and choose a membership level suitable for you. Every little bit helps us produce the great content and further our mission. Also, why not consider becoming a member? Choose the membership link here, click it, put your name and your first name and your email, and you'll be added to our list. You'll receive a comprehensive digest of all our videos and articles and all our great content. Joining and becoming a patron helps us grow and improve and more fully realize our mission. Thank you. This is Dr. Jim Daly for Astronomy for Change. Until the next video, please stay well and keep looking up.